Good afternoon and welcome to the Morrison Planetarium Tour of the Universe live stream for today, November 30th, 2022. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and thank you to everyone joining us from, seems, all around the world. I know we have a few people from the UK taking part in our live stream today, coming at you from the Morrison Planetarium Facebook page as well as the California Academy of Sciences Facebook page. I'm coming to you from deep inside the bowels of the California Academy of Sciences, in fact, directly below Morrison Planetarium. If you've joined us in the past several weeks, you may have joined one of our simulcasts from Morrison Planetarium, where at this time slot, Wednesdays at 4:30 p.m. Pacific every week, you can experience what everyone in Morrison Planetarium is experiencing as we tour the universe from here on Earth and the International Space Station, which is what we're seeing right now, on out to the edge of the observable universe. Today, and for the next several weeks as we go through the holiday season and into January, we're doing things a little differently. We're actually going to be hosting this kind of live and a little more interactively. And at least today, we've got different presenters lined up for the next several weeks. If you have questions that pop up during the course of our tour, I do want to get us all the way out to the edge of the universe, like I said, but if I have time and if we have a good question, we can pose those in the chat, and I'll do my best to answer a few of those as we make our way through the universe. But with that said, I'm going to go ahead and disappear from your screen and start piloting you through our three-dimensional model of the universe. I'll also note that this is software that we are actually working with the developers to provide free of charge to anyone who wants to download it. The software is called OpenSpace, and we'll talk about it more maybe at the end of the program, but you can actually replicate this experience yourself with data that's built into the software. And what's really cool about this is that it's actual data. So you may have noticed, if you're looking closely at our clouds here, they're kind of pixelated, and maybe if you look really closely along this kind of diagonal line cutting through the screen, there's even what looks like a little bit of a seam between the clouds. It's not quite a perfect representation like we're used to from Hollywood films and such. But as I pull away from the International Space Station, you can see that in a little greater detail. And the reason for that is because we're actually showing data from just a day ago. This is the actual cloud patterns photographed by satellites in orbit around Earth, and that's representative of what we're going to be showing throughout the course of today's program. But before I leave the space station behind entirely, actually, let me go back and just give you a little bit of context for where we're going during the course of our show today. Like I said, this is a virtual tour of the universe, so we're able to take you out to places observed by our largest observatories on Earth, much farther than humans have ever traveled out into space physically. So the International Space Station is a great example of how far humans go out into space these days. It's in orbit around Earth, a few hundred kilometers above Earth's surface, and this is where astronauts have been going for the past several decades. Only about 50 years ago did humans travel farther out into space, and now the U.S. and other countries are proposing returns to the moon, the farthest point that we've traveled out into space. But for right now, and actually to give a little context here, let me go ahead and put up the orbit of the International Space Station as we pull away from Earth. Right now, this is as far as we travel into space. So as we go farther out into the universe, we're going to be relying on, as I mentioned before, observations from telescopes out in space, here on Earth, and a model, a three-dimensional model of the universe that has been assembled over a period of decades, using the latest astronomical imagery and data to present, as accurate as we can, a three-dimensional representation of what's out there. So here's our Earth, with the International Space Station in orbit around it. And let me now begin to take you out into the farther reaches of space. Now, you couldn't, of course, actually see the orbit of the ISS if you were to be out in space looking at Earth. Similarly, I'm going to use some diagrammatic elements to sort of give a sense of how large and how far apart things are. So let me just go ahead and add some of those now. you'll see a line connected to Earth. That's Earth's orbit around the sun. And now you'll also see this kind of orbit encircling Earth, and that's actually the orbit of Earth's moon. So I mentioned, as far as humans have traveled out into space, initially back in the 60s and 70s, it was 12 lucky Americans who got to make the trip. But now America and other countries are planning returns to the moon. That is as far as we've traveled, though. And to give a little bit of context, that's about 400,000 kilometers from Earth to the moon, or if you prefer to think in miles, about 240,000 miles. So if you were to imagine owning a car and driving it for years and years and years, you might eventually put 240,000 miles on a car. So if you think about that, that's how far away the moon is. Astronauts made that journey in about 4 days from Earth to the moon. But the distances that we're going to describe throughout the course of this program are much, much greater. So now let me pull around, and in addition to Earth's orbit around the sun, we can see other orbits of other planets around the sun. And I will pull away far enough now so that you can see the sun kind of come into view on the right-hand side of the screen. So the sun is about 150 million kilometers away, 93 million miles. And that, in terms of a yardstick that we're going to use throughout the course of the show, is about 8.5 minutes in terms of light travel time. Light travels at essentially constant speed in a vacuum, 186,000 miles per second, or 300,000 kilometers per second. So it traverses that 150 million kilometers, or 93 million miles, in 8.5 minutes. Now, for comparison, actually, if you go back down to Earth and the Earth and Moon system, remember I mentioned that the Moon is about 240,000 miles, 400,000 kilometers. Those are big numbers. If you want to think about it, it's a second and a half in terms of light travel time. So you could think of that as like a pause in conversation. That distance from Earth to the sun, 8.5 minutes, maybe that's more like a quick lunch. If you're really in a rush and you need to grab a bite to eat before you go back to work or whatever, maybe you can do that in like 8.5 minutes. So already that's a vastly greater distance. That hard to imagine distance of 240,000 miles, 400,000 kilometers, that distance that you might drive a car over the course of its lifetime, is pretty far, traversed in a second and a half in terms of light travel time. And then the sun is many times farther. And now, in just the few minutes I've been talking, we've pulled away from our view of the solar system. And now we see the orbits of the 8 planets. And if you're older than a certain age, you may have learned that there were 9. There are 8 planets now officially. And those 8 planets are worlds of their own right. We could spend easily a hours talking about those individual planets. But I want to give you a context of the entire universe. So let's just try to put, in terms of the scale of the universe, let's try to put our solar system, our collection of planets in orbit around our sun, into context, at least in terms of size. So one thing we might think about is the parts of our solar system that we have explored. And indeed, we've sent spacecraft out into the universe to explore. But our fastest nuts and bolts spacecraft have never made it outside of our solar system. So I want to show you the 5 fastest spacecraft that we've ever built. Now, there are other spacecraft. We've sent probes to Mars. We've got spacecraft in orbit around Jupiter right now, sending back amazing and beautiful images. Those aren't included in this. These are the 5 spacecraft that are on trajectories that will take them outside our solar system, and they're the 5 fastest nuts and bolts objects that we've ever built. So we have the Pioneers 10 and 11 spacecraft, and then Voyagers, got to look closely, 1 and 2. And then we also have the New Horizons, I think I mispointed it out incorrectly, the New Horizons spacecraft. Now, the Pioneers and the Voyager spacecraft, the first 4 that I pointed out, were all launched back in the 1970s. The New Horizons, this kind of straight line heading zipping right out to visit, as it turns out, the former planet Pluto. was launched in the early aughts, so much more recently. But all 5 of these spacecraft have achieved escape velocity from our solar system. And we're projecting their locations out to where they are right now. So if you could see their trajectories and relative to our solar system, you could begin to see how far they've traveled over the course of about 50 some odd years in the case of the Voyager spacecraft, and in a couple decades in the case of the New Horizons. Since we've used light travel time already, let me try to put that into a scale using our solar system as a guide. That orbit of Neptune, which is the largest orbit, so it's the most distant planet from the sun, and thus has the largest diameter in terms of its orbit. That's about, it's a little less, but it's about 8 light hours across. So if you remember, a second and a half of light travel time to go from Earth to the moon, 8.5 minutes to go from Earth to the sun, or vice versa. It takes like 8 hours to go across the diameter of the solar system as measured by the size of Neptune's orbit. Now there's a lot more in the solar system than that. The sun has magnetic fields. We know that there are clouds of comets that are much, much farther than Neptune. And of course, Pluto itself, the poor little former planet that I keep mentioning, is farther out than Neptune for most of the time it spends orbiting the sun. But for these purposes, we can think about the diameter of our solar system in this sense being about 8 light hours. And now, if we want to talk about the distance to the nearest stars, we're talking about distances of light years. So it takes 4 years for light to travel from the star nearest the sun to be observed by our telescopes here on Earth. That's the closest star. Many of the stars that we see here, we're exaggerating their size and brightness to make it kind of easier to spot them. Many of these stars are much, much farther away. So again, let's try to put this in scale. Now, I'm going to pull away from the sun, and as I do, those trajectories of the fastest spacecraft we've ever built are going to shrink down, and we're also going to brighten the sun so it's shown consistent with the brightness of the other stars in our data set. And you'll notice, as I've pulled far enough away, if you look at this star, it is going to begin pulling away from its location in, if we observed it from Earth, in the constellation Canis Major, the big dog. And now we've traveled so far from home that in fact, even though these stars are separated by light years, they are beginning to shift in position as we sort of drift through space, orbiting the sun's location. So this reinforces the idea that what we're looking at here is a model, a virtual model of the universe. It allows us to do things like break the speed of light, in fact, shatter the speed of light, because we've traveled, in this short period of time that I've been talking, we've traveled tens of light years out into the universe. And of course, that means it would take years for light, the fastest thing in the universe, to travel that same distance. So as we continue to expand our perspective here, let's give a little thought to these other stars that we're seeing. We're watching them kind of drift slowly across the screen. These are stars as big as, or many of them, some of them bigger, many smaller than our own sun, than our own star, the sun. And each one of these stars has, for the most part, has planets in orbit around it. We have discovered thousands of planets in orbit around other stars. And so if we could just sort of circle all of the stars that we know to have planets in orbit around them, this is the kind of collection of circles that we'd see just in the universe relatively close to home. Now, most of the planets that we've discovered are in fact close to home because it's hard to spot the signs of small, tiny planets in orbit around their relatively large and massive parent stars. And yet, we know that it seems like most stars, if not basically all stars, have planets in orbit around them. So planets are a very common occurrence in the universe around us, and it's an exciting development in astronomy that over the past couple decades we have discovered more and more of these worlds in orbit around other stars. every one of these stars, many light years away, too far, vastly farther than any of our spacecraft have traveled, and yet, in the scheme of things, relatively close to home. I'm hoping that actually these will come into view here. So these planets have been discovered using different methods. But you'll notice a kind of rising in the lower left-hand portion of the screen here. We have a large collection of these little circles denoting stars with planets in orbit around them. Now, what we're doing is the circles are kind of floating in 3D space. So a larger circle means that it's closer to us, a smaller circle means it's farther away. So these small circles are kind of receding into the distance because the markers are, in our virtual model of the universe, are receding off into the distance as well. These thousands of planets were discovered by the Kepler mission, a system that was designed to find basically the shadow of planets passing between us and their parent star. So we've got a large collection of these exoplanets that we've found relatively close to home, and because we systematically studied the part of the sky that's kind of drifting off and above to the left, we found many more stars, many more planets around stars in that part of the sky. But before we get too far, I just want to kind of leave our collection of planets with one thought. And that is that if we think about planets, it's easy to think of things like Star Trek, or think about the science fiction that has described to us for many decades the idea of planets in orbit around other stars, inhabited by life forms, and the excitement of thinking about the potential of life is sort of a natural outcome of thinking about the existence of these planets. As it turns out, we haven't found a lot of planets a lot like Earth, and we've certainly not found planets that are exactly like Earth, but the potential seems to be there. So it's exciting for astronomers as well. But if we want to think about like which of these planets could have maybe detected signs of life on our own planet, we want to then think about flipping that around and looking for life on other planets. We could think about how we humans have actually searched for life in the universe around us, and that is by searching for radio signals. So this sphere that I've just put up is centered on the sun, and it has a diameter of roughly 80 light years. Now, that was chosen because we first began broadcasting radio waves that are strong enough to escape Earth's ionosphere right before World War II with the invention of television. And although aliens are not going to be watching I Love Lucy, they would be able to detect a radio signal that was distinctly not natural, not a phenomenon that we observe emitting radio waves in other parts of the universe. And since radio is a form of light, it travels away from Earth at the rate of 1 light year per year at the speed of light. So the radius of this sphere centered on the sun, and effectively therefore on Earth, is about 80 light years, roughly equivalent to the period of time that we've been emitting radio signals strong enough to escape Earth's ionosphere and potentially strong enough for a hypothetical alien civilization to detect. So if we think about this, that means that all of the circles that you see inside the sphere here, if they happen to have an intelligent alien species who could build radio telescopes living on them, they could turn their telescopes toward Earth and maybe detect a signal from our species, from humanity. But it also means that all of these circles that reside outside of that sphere have no chance of hearing from us, at least not right now, because our radio waves, our radio signals have not washed over them just yet. So they'll have to wait years before our radio signals have the time to reach them. And then, again, it's only if we can imagine an alien species looking back on us that we could imagine being in contact with a hypothetical alien species around one of these worlds, around one of these stars highlighted by the individual circles. So if you want to think about it, this sphere, what we kind of sometimes call the radiosphere, it's a little bit like our electromagnetic footprint in space. So the same way those trajectories of the Voyager spacecraft, the trajectories of those fastest objects we've ever built, are speeding outside of the solar system, those represent kind of our physical footprint of our species in the universe around us. This sphere, again, about 80 light years in radius, represents our electromagnetic footprint in the universe. So let's compare that to the size of the sort of city of stars that we live in, our galaxy. Now, you can see along the right-hand side of our image this hazy band of, it's actually quite bright in our representation, that represents the band of our Milky Way galaxy. And it's called that if you go out into a nice, clear, dark sky, you can see the Milky Way. It's the way our galaxy appears from the inside. It's the light of hundreds of billions of stars, because that's how many reside inside our Milky Way galaxy. Hundreds of billions of stars kind of smeared together, because most of them are faint and distant, to form this hazy band that crosses through our night sky. And what I want to do here is point out, again, this is our footprint in the universe around us, our electromagnetic footprint. I'm going to back away. There's going to be some dots that appear in the background. I'll talk about those in a moment. But I want you to take a look at this galaxy that you see in front of us, the Milky Way galaxy, with a diameter of about 100,000 light years. So it takes about 100,000 light years for light to travel from one side of our galaxy to the other. And our kind of technological footprint in all of this is visible as this tiny collection of pixels at the center of the screen. So if you think about now light travel time, when we started by talking about a second and a half of pause in conversation to 8.5 minutes, a quick lunch, 8 light hours across our solar system, which I didn't say, but you can think of it as a good night's sleep. 4 light years to our nearest star, a high school or college education. Now we're talking about an astronomical object that is 100,000 light years across. That's roughly the age of our species on this planet. And the distance between our sun and the center of our galaxy is about 35,000 light years. And if you think about what humans were doing 35,000 years ago, we were painting the insides of caves. So even our metaphor of distance, it's more than a metaphor, but the way of framing distance in terms of light travel time, which seems so handy and familiar when we were starting the journey, we're already encountering as mind-bogglingly large when we get to even the size of our home galaxy, our collection of hundreds of billions of stars that we call the Milky Way. But now, I want to point out that in the background, the little circles that you see are, again, markers, and each one of them represents the location of another galaxy. Now, for the most part, these galaxies are a little smaller than our Milky Way galaxy. You can see 2 here, the Large and Small Magellanic Clouds. These are 2 much smaller galaxies in orbit, essentially, around our own Milky Way. And these other points, again, represent individual galaxies. Some of them may be as small as the Large or Small Magellanic Cloud. Some of them may be as big, and a few even bigger than our own Milky Way galaxy. And I want to wrap up our program now by taking you much, much farther from home. You'll notice that these individual dots are kind of clumped and clustered together. We live in kind of a cosmic backwater, to be honest. It's not a particularly crowded part of intergalactic space. If you look over here to the left, this clump of points is the Virgo cluster. It's a cluster of galaxies relatively close by. It's about 65 million light years away, which means that when light was leaving galaxies, when we observe a galaxy in the Virgo cluster, we're seeing light that's 65 million years ago. It means that it left its parent galaxy around the time that the dinosaurs died off on Earth. This clumping and clustering of galaxies was important for us to begin to think about how all of this took shape, and some of the more points kind of popped on here. What we're doing is actually interweaving multiple surveys of galaxies. And the process, much like the process of finding exoplanets, the process of measuring distances to galaxies is challenging, but we've kind of automated that process. And as an artifact of the way we determine distances to galaxies, you'll notice that some of these kind of bright lines of points sort of seem to point back to Earth. Now, it would be kind of both tempting but quite arrogant to think that those are actually physical phenomena in the universe around us. All of these galaxies sort of pointed back at Earth as if some kind of cosmic wayfinding. But instead, it's because of the way we're making the observation. The distance error, basically, we can find a cluster of galaxies, but the distance error means that the cluster, which would be a clump of galaxies like the Virgo cluster, gets stretched out along the direction or line of sight. So basically, we're observing each one of these points, each one of these galaxies from our location here in the center of our model of the universe, not the center of the universe, but our center of the model of the universe. And because of our vantage point, our errors in estimating distances create these artificial structures in our virtual representation of the universe that suggest everything pointing back to home. And you'll notice that there are a lot of parts of the image that are kind of not filled in. Again, this goes back to the fact that it's hard work to determine the distances to these galaxies. And although we've automated that process, which is why we have so many points in the model that kind of fills the upper half of the left hand of the screen, there's still parts of the universe that remain to be explored. We're still filling in and making observations that will create a fuller representation of the three-dimensional nature of our universe. But I want to end by pulling far enough away that we'll actually see, and I apologize, I think probably some of these points are kind of flickering, but again, every one of these points represents an individual galaxy. And I was hoping that we would see, here we are. And the punchline to this is this image that's appeared as kind of a backdrop. And this is where we really had to confront this idea of light travel time that we used as a measuring stick toward the beginning of the program. When we think about light traveling at a constant speed, which allows us to use it as this handy yardstick to measure distances in the universe, it also means that light is traveling at a finite speed, and our universe is not infinite in age. The universe, as far as we understand, started about 13.8 billion years ago, and as we look farther out into space, we're looking farther back in time. And the punchline for this is this kind of cosmic wallpaper that I'm putting up as a background. So here in the center, we have all of these galaxies that we've observed and measured the distances to over a long period of time. And this cosmic microwave background that we're using in the distance is the oldest light in the universe that we can collect. It dates back to an age when the universe was, in fact, kind of contradictory to the way we're showing it here, much smaller and denser. And this is the first light that was created that could travel the immense distances to be observed by us today. So this light dates to an epoch about 400,000, give or take, years after the Big Bang, after the beginning of the universe. So 400,000 years into that 13.8 billion year history that we are living through. And the modeled appearance is actually a variation in temperature of the cosmic microwave background. The dark parts are a little bit cooler, the bright parts are a little bit warmer, and it turns out that the dark parts are a little denser than the warm parts, and they collapsed to form the clusters of galaxies like the Virgo cluster that I pointed out close to home. And they gave us that lumpy structure of the universe around us. So these fluctuations in the early temperature and density of the early universe gave us the structures that we see close to home. And yet, surprisingly, the variation from the darkest parts, the coolest, densest parts, to the brightest, hottest, least dense parts, is only about 1 part in 100,000. So that tiny variation, that tiny fluctuation, we kind of pumped up the contrast on this image. That tiny fluctuation was enough to bring together the structure of galaxies that we see close to home. So that's kind of the big punchline for our tour of the universe. And the last thing I want to mention before we head home is something that's a little strange when you think about it. I mentioned it briefly a moment ago. But again, we're kind of down here in the center of this model of the universe. And this is actually a model in space and time, because as we travel back home, we're traveling essentially from the past to the present. We appear at the center of this three-dimensional virtual model of the universe because we're the ones drawing the picture, because we're the ones plotting the distances of these objects away from us. So it's not that we are the center of the universe, but rather that in this depiction of the data that helps us understand our universe, we lie at the center of our virtual universe, our virtual collection of data. So with that heady thought, we're going to go ahead and come back to our home galaxy, the Milky Way, the large and small magical clouds you can kind of see there in a distance. We still have our image here, our sphere that represents our most distant radio signals. I'm going to go ahead and get rid of that as we come closer to home. And then we'll travel through the stars closest to our own to finally encounter the sun. And as we come back again, we'll see our orbits of the planets around our parent star, the sun. We'll come in close to the third rock from the sun, our own home planet, Earth. And I really want to thank you for joining us today during our tour of the universe. Happily, we're able to take you from Earth out to the edge of the universe and safely back home. I hope if I didn't see any questions pop up on screen, but if you have any questions, please feel to pose them in chat, and we'll be happy to take a stab at answering them. But meanwhile, thank you for joining us at for this tour of the universe, and I hope you have a great rest of your day.